Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and now we are going to start a new module of this course, that is process management. So this is the second module of this course, and we just finished with the first one. It was an introduction module, and there we talked about what is an operating system. So now we understand that the operating system is a special piece of software that is responsible for managing the computer hardware. And if you talk about the different hardware components that are there, then the most basic and fundamental hardware component is the CPU. And in this module, this second module of process management, we are going to focus on the CPU and understand how the operating system manages the CPU and makes it easy and efficient to use by providing the concept, the abstraction of a process, right? So as you can see, this second module of process management has been split into 6 different topics. The first topic is process introduction. So in this topic, through a series of videos, we are going to understand what is a process and how the operating system implements this abstraction of a process over the CPU. Although we have already talked about the process in the previous module, but here we are going to look at it in more detail. So without further ado, let's get started. So in order to understand how the operating system manages the CPU, let us quickly recall the responsibilities of the operating system with respect to the computer hardware. So if you talk about any piece of computer hardware, then the operating system has two fundamental duties that it has to play. The first one is to make sure that the hardware is easy to use, and the second one is to ensure that the hardware is used in an efficient manner, right? So if you talk about making any piece of computer hardware easy to use, there the operating system accomplishes this task by providing the concept of an abstraction. So what is an abstraction? So basically, as we already studied in the previous module, there are several hardware resources in the system. There is a CPU, memory, the IO devices. All of these are physical resources, right? So what the operating system does is that it creates a virtual resource on top of the physical resource. And this virtual resource is much more easy and powerful to use if you compare it with the actual physical resource. So this is the idea behind abstraction. And as we already know, the abstraction that the operating system provides in the context of CPU is the process, which is the topic of this video, right? So there are other abstractions also. For memory, the operating system provides the abstraction of an address space. For IO devices, there is device drivers. For storage devices, there is files and directories. So all of these are abstractions, right? And finally, talking about the second responsibility, the second duty, that is to make sure any hardware is used efficiently. There, the operating system has to do a careful resource management. So there are several resources in the system, and all of these are required by the computer applications. And these are shared and limited in nature, right? So what the operating system has to do, it has to keep track of all of these resources. And whenever the computer applications make a request for these resources, then the operating system has to carefully allocate these resources to the computer applications. So this is how the operating system manages the resources and make sure that they are used in an efficient manner. So now what we are going to do, we are going to focus on the first responsibility, that is making the CPU easy to use. And we are going to see the abstraction that the operating system provides, that is of a process. So now let us understand what exactly is a process. So now let us talk about the process. So as we know that the process is an abstraction that has been created over the CPU in order to make it easy to use. So first of all, let us quickly recall what is the underlying problem or the challenge with using the CPU. Then we can understand how it is made easy to use, right? So the problem with the CPU is that in any modern computer system, the number of computer applications, as you can see here, the number of computer applications that are there in the computer is way more than the number of CPUs that are available in the system. So just to give you an example, here I have taken a hypothetical computer system. Here there is only one single CPU, and on this one CPU there are n different programs that want to run, right? And this number is way more than one. So this is a typical scenario in any modern computer system, that the amount of programs that want to run on the CPU is way more than the number of CPUs. So the problem with this is that the way the CPU has been designed, it can only execute a single program at any given point in time. So at different time instance, there may be different computer applications running on it. But if you talk about any single time instant, then only a single program can execute on the CPU, right? So this is the challenge, that how do we run so many different computer applications on limited number of CPUs, right? So as we already know, the way we solve this problem is by the concept of time sharing. So what is time sharing? Basically, here as you can see, there is a single resource, that is the CPU time. and there are multiple entities that want to use this resource. So the obvious way in which this will happen is that all of these applications will have to share the CPU, and this sharing is called time sharing. Here what happens is that the CPU is allocated to each of the different programs for brief amounts of time, right? Every program gets to execute on the CPU. It will execute some instructions, and then after some time the control of the CPU is then transferred to some other program, right? In this way, the control of the CPU is frequently switched among the different computer programs, so that each of them gets a shot to execute on the CPU and can make progress. So the CPU time, if we share it among the different applications, then we can allow multiple programs to run on the CPU. So the challenge that was there, that is how do we run so many computer applications on limited number of CPUs, that is solved by the concept of time sharing. So this concept of time sharing that we just discussed, now the question arises that who will implement this time sharing mechanism? The computer applications themselves cannot do this, because if you think as a programmer, then when you're writing your computer applications, you have this mental model that your program will have the control of the CPU for its entire duration, right? You don't think as if the control of the CPU will be taken away from your program, right? So there has to be someone who will implement this time sharing mechanism, and as you can see from this figure, that it is the operating system that implements this time sharing mechanism for all the different applications that are there in the system. So it's the responsibility of the operating system to share the CPU time between the different applications. Now, the very first thing that the operating system must now do is that it must be aware of all the computer applications that are there in the system. Then only it can share the CPU among them. So the operating system has to keep track of all the running programs in the system. And this concept of a running program is what we call a process. So what is a process? It's a very simple thing. It's a running program. And in a computer system, there are several processes. That is, there are several running programs that want to use the CPU. So that is where the operating system will model all of these running programs, keep track of all of them as a process. And now the problem boils down to time sharing the CPU among all these processes. So first of all, there must be a mechanism so that the operating system is aware of all the different programs that are running, that want to run, and it has to then share the CPU among all these processes. So now let us take an example and see how this time sharing is implemented by the operating system in practice, right? So now we'll see an example and see how the operating system implements it in a computer system. So here we have a hypothetical computer. There is a single CPU on this computer and it has three running programs. So as you can see, there are three processes, P1, P2, and P3. Now this is the operating system. It has to keep track of all these three processes and then implement the time sharing mechanism for this CPU among all these three processes. So what the operating system does, it picks any one of these three processes and lets it run on the CPU. So as you can see, let's say it chooses process P1 and allocates CPU to process P1. It allows that particular process to run for some time. It will execute its instructions for some time. Then what the operating system does is that it takes control of the CPU from process P1, and then it will assign it to some other process, because all the processes should get a chance to execute on the CPU. So as you can see now, let's say the operating system picks process P2 to execute next. So just like process P1, it will execute for some time, and then the control of the CPU will be taken away from process P2 and given to some other process. So now let's assume that it is given to P3. So now you understand what is happening here. Each of the processes gets to execute on the CPU for some time, and then the control is given to some other process. So in this way, let's say then P2 goes next, then let's say P3 goes again, and finally P1 is allowed to execute on the CPU. So as you can see, this horizontal axis, that is this is the CPU time, and as you can see, it is literally being shared by all the different processes. So this is P1, P2, P3, and so on. So these three processes are sharing the CPU time, and if you notice that no single process is allowed to execute on the CPU for the entire duration. Each of them get a fraction of the CPU time, but nonetheless each of them can execute few instructions and make progress, right? So this is how the operating system shares the CPU between all the different processes in the system. So this is the concept behind time sharing. And as you can see here, the operating system has to keep track of all the different running programs, all the processes, and then only it can implement this time sharing. Now, another point is that as you can see, now we as a user don't have to worry about the number of CPUs that are there in the system. Whenever we want to use the CPU, all we have to do is launch our program, and the operating system, from the operating system's perspective, this running program is a process, and it's the duty of the operating system to ensure that that running program, that process gets a fair share of the CPU. So from the user's perspective, using the CPU is easy now. They just have to launch a program, and they can be ensured that whichever program that they launch, it's the operating system that will take care of assigning or allocating the CPU to their program. So this is how the challenge that we saw, that is how can we run so many different computer applications with a limited number of CPUs. This is how the operating system solves that problem, by modeling each running program as a process, right, and making the CPU thus easy to use. So now we have a good idea of what is a process. We understood the problem that we wanted to solve, that is of running multiple programs on limited number of CPUs. Then we saw the concept of time sharing, and finally we understood how the concept of process uh, helps us in dealing with this problem. So now what I want to do, I want to actually clear out the difference between the different terms, that is a program and a process. So till now, I have been using these terms quite interchangeably, but there is a clear distinction between the term that is a program and a process. So let us define these terms concretely. So it all starts with the source code. As a programmer, whenever you want to write an application, the first thing that you do is that you write your code in some high level programming language like C, C++, Java, Python, and that piece of code that you write in a high level language is called source code. Now, after you have written the source code, the first thing that you have to do before you can run it, you have to compile this source code into something that the machine can understand. So this source code is written in a high level language, which is quite similar to natural language, that is English, right? And this is something which the machine won't understand. So in the second video of the first module, right, there we talked about the language of the machine. That is, the machine, the computer basically only understands zeros and ones, right? It cannot understand anything else. So the first thing that we have to do before we can run this piece of code, we have to convert this into a binary format, right? And that binary format is called a program. So as you can see, we have to compile the source code. And when you compile the source code, basically what happens is that a set of instructions as well as the data that is there in your program is generated. And they're bundled together into something that is called a program. And all of these instructions or data are in a binary format. That is, it's only zeros and ones, as you can see in this picture. So you have compiled your source code that was written in a high level language, and now it is in a binary format. So this is something which the machine can understand. It has a bunch of instructions and some data. So these instructions will be executed, and that is how your program works basically, right? So the first thing you have is the source code, then you get the program. So till now, we haven't yet run the program. This is just a binary file. So let me properly define this. A program is basically a binary file consisting of executable code and related data. So I said instructions. So executable code and instructions mean the same thing, right? So this is a program. This is a just a binary file. Now, the next thing that you have to do is that now you can run this program. And when you run this program, that is when it becomes a process. So as we already discussed, that a process is a running program. The actual definition is the process is a running program. And when a process is running, then it's an activity that is going on. The instructions that were present in your binary file, that is this program, these are getting actually executed. Here, nothing as such, any activity was not going on. Here, it was just a binary file. When you run this program, that is when some activity is going on, some instructions are being executed. The user will be interacting with the running program, the process. They will be giving some input, they will be receiving some input. So this is the difference between a program and a process. We often kind of use them interchangeably, but there is a clear distinction between what is a program and what is a process. A program is just a file, it's a passive entity, and a process is a running program, it's an activity that is going on. And we write programs so that we can run them, right? Only when you run the program, then it becomes useful, it does something useful. So this was a clear distinction between a program and a process. So now what we will do, we will see a small demo, through a practical example. We see how we go from source code to a program, and how a process looks like in the operating system. So let's see that demo. So let us start the demo, and in this demo we'll see how we go from source code to a program, and finally a process using a simple example. So here I have a source code written in C. It's a simple hello world code. As you can see, there is nothing much. There is this main function, and within this main function, we have a while loop. It is an infinite loop, and what we are doing here, we are printing a hello statement, and after that, we are sleeping for 1 second. So this is a very simple code where we are infinitely printing the hello statement and then sleeping for 1 second. So this is the source code that we have. So if you want to run this code, first of all, we need a program. So at this point, we don't have the program file yet. We only have the source code written in C. As you can see, this is a C source file. So in order to get the program, we'll have to compile it. So let me open up the command prompt and we'll then compile this source code. So we'll navigate to this directory. And if you list out the contents of this directory, so you can see we have the hello underscore world.c file. So let's compile this program, compile this source code and get the program. So in order to compile this source code, the command we use is the gcc command. So gcc is the gnuc compiler. You then have to give the name of the source code, and after that you have to give the name of the program. So -o. Yeah, so the name of the program that I'll give is hello underscore program. So hit enter, and if you list out the contents again, you can see we have a hello underscore program .exe file. So what is a .exe file? .exe means it's an executable. It has executable code which the CPU can execute. It has instructions which the CPU can execute. So this is the program file that we wanted, and you can see here also we have the program file. So there are two ways in which we can run this program. The first one is via the command line. So here we can type in the name of the program, that is hello underscore program dot exe, and hit enter. So as you can see, our program is running, and this is when we can say it's a process. So this running program that you see, the statements that are being printed, it's also sleeping for 1 second. This activity, this running program is a process. So compare this with the program. The program is just a passive file. This is hello underscore program. This is just a file. So we started with this C source code. We got this program file, and when you run this, that is when you have a process. So if you want to see this process, then you can go to the task manager, and within the task manager, you search for the name of your process, that is hello underscore program, right? So this is the process. You can see the resources that it is consuming. Some of CPU is there, memory, disk, network. So this is our process. And if you go to the details pane, here you'll see some more details. For example, the process ID. So the process ID is a unique identifier that is assigned to each process in the system. You can see the status as running, the user which has launched it, and several other attributes associated with this process. And if I kill this process, let's say I end this task, you can say, do you want to end hello underscore program? And you say end process. If I end this, you can see this program just terminated. So this is how the process looks like. And as I said, there are two ways to launch a process. We compiled our program. We can also double click via the GUI interface. We can just double click this, and we will have a process. And just to verify again, if you go to the task manager, if you search hello, you can see our hello underscore program is running. So this is how we have the source code. Then we got the program file, and then after running that program, we got the process. So these are the three different things, and how we go from one to another. Another very important point that I want to talk about is that using a single program file, we can launch it multiple times, and every time we launch that program, each of that instance is a different process, right? So let me show that with an example. So we just created the hello underscore program executable file, right? This is the program, and the point is that we will whenever we launch it, each time when we launch it, it will be a unique instance. It will be a unique process. So to illustrate this point, I have opened 4 different terminals for you, and in each of these terminals, I'm going to launch the hello underscore program.exe program that we just created. And the point is that these 4 instances, all of this will be unique, right? So let me start the programs. So as you can see, we have now 4 different copies of the same programs running at the same time. So as you can see, hello is being printed, and it is sleeping for 1 second in each of these terminals. And if you go to the task manager and find out the processes that we just launched, you can type hello underscore. Yeah. So if you see here in the details pane, there are 4 different processes that are running, and each of them have a different process ID. They have a unique process ID. So the point is, we have a single program file, and now four unique processes that we just created out of that one single process. So out of that one single program. So this is how basically whenever we download any piece of software, we get the executable file, and we use that particular executable file multiple times to create a different process each time we want to run the program. So this was another important point. So now that we have understood what is a process, we can start studying how the operating system implements this abstraction of a process over the CPU. So the way I have organized this module is that there are two parts to this module. As we started this video, we said that the operating system has two fundamental duties with respect to any piece of hardware, right? So when it comes to managing the CPU, it has to first of all make it easy to use, and then ensure that the second duty is to ensure that it is used in an efficient manner. In the same way, I have divided this module into two parts. In the first part, we will study how the operating system implements this abstraction of a process. So now we have just understood what is a process, but we don't know how the operating system implements this abstraction. So the first half of this module will spend some time understanding and talking about the different aspects of a process. And once we have a good idea of the process, then we'll shift our attention to the second duty, that is making sure that the CPU is used in an efficient fashion, and there we'll see how the operating system manages the CPU as a resource. So if you see this time sharing diagram here, also you can see that there are two parts to this process management. The first part is that first of all, the operating system has to be aware, has to be able to keep track of all these processes, right? Once it has the knowledge of these processes, it is tracking these processes, then only it can do the time sharing. So the second part, that is once it has implemented this abstraction of a process, then it has to do this time sharing, right? It has to allocate the CPU to these different processes. So understanding how the operating system implements this time sharing will be in the second part of this module. So in the initial part of the video, I explained that this module has been split into six different topics. So the first four topics here, we'll spend time understanding how the operating system implements this process, and there are several other aspects that are related to a process which we'll talk about. And finally, in the last two topics, we will discuss the time sharing and how the operating system allocates the CPU to the different processes. So there are several policies that are called CPU scheduling policies, using which the operating system decides which process will be running on the CPU. So this is the brief layout of the module, that is process management, which we are going to study. So guys, this was it for this video. In this video, we studied what is a process, we formally defined it, and we saw some practical examples also to understand, to clearly distinguish between a source code program and a process, right? And now we are ready to start understanding how the operating system implements this abstraction of a process, and overall in the process management, how the operating system manages the CPU. So guys, this was it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.